Hi, we're here today to talk about probability current for the 1D time-dependent Schroedinger equation. And it's my first introduction to it, so if you're in my course, this may be the first time you've heard of it. I'm writing this for a specific course, the regular junior senior level quantum mechanics course in the American undergraduate physics curriculum. We call it Physics 460 at my university, Dominguez Hills. I don't cover this material when I teach the prerequisite course, the end of the intro sequence, but frankly, everything I'm going to do in this video, you should be able to follow if you're actually in the prerequisite course for this. It should not be difficult material to follow. So I don't think you know this material, but hopefully this should come off as fairly easy for you. You need to be comfortable with the Schroedinger equation. You need to know partial derivatives really well and how to do them. And of course you need to do some simple complex algebra. There's not really all that much. I should note that different courses sometimes do some subtopics in different order, and I tend to cover this a little bit early, so I'm doing it in a kind of abstract way that may not seem like it's really relevant to you yet, and frankly it doesn't have to be. But we'll cover it a lot more later in the course when it's really important, and I'm doing it now partly because I think it ties together some of the math we're doing. So without being fully rigorous, I can still show that we're doing a mathematically consistent thing with this course. So we're going to start out with something we know well. We often say that probability is the absolute square of the wave function, or psi star psi. We should really say the probability density function, because that's a function of space, right? And space and time is equal to that product, psi star psi, the absolute square of the wave function. I'm going to need, for what I'm doing, the time derivative of that, and I know how to do time derivatives. It's a partial derivative with respect to time. I just use the product rule, and I get first term times derivative of the second plus second times derivative of the first. And that's all I can do without knowing what the wave function is. Now I'm going to define a new function that I call j here. And it's got some prefactors that'll make it work out right magically, of course. And it looks kind of similar, but these are space derivatives, and note there's a relative minus sign between those two terms. That's important. So this is not directly a derivative of the probability density function because of that minus sign, but it looks a little bit like one. What I'm going to need for that is the space derivative of it, which I do the same way. And of course the product rule should give me two terms for each of these two terms, but the other two terms are both the space derivative of psi star times the space derivative of psi, and then minus the same thing in the other order. So the other two terms cancel. So I didn't ignore them. They go away. They cancel each other. I'm going to go really, really slowly through the next few slides to get to the bottom line, just to make sure I'm consistent and complete here. Starting with the Schroedinger equation, if I clean things up, I move them around, I don't put all the variable dependence in explicitly, I'm going to need this d by dt of psi, and I'm going to need the complex conjugate of that. So I'm going to complex conjugate that whole equation. And to do that, of course, I complex conjugate each function, and I change the i's to negative i's, right? And the complex conjugate of a proper equation is a proper equation. It has to be. When I do this, I would note that I've seen some books that do this and they don't explain. They look like they're ignoring the potential in the Schroedinger equation. They're not. They know what they're doing. I know what they're doing. But if it's the first time you see it and they appear to ignore it, they should explain why. They're right. The potential term drops out, but I want to show you instead of just saying that. Remember that it's a real function of space. That is, it's not complex. The potential is a thing that cannot be a complex function for anything you do at this level. Excuse me. The time derivative of the probability density function, that was something we said we needed a few pages ago. I can write that out. And when I take what I had on the previous to previous page for the time derivative of psi, I'm going to stick that in there. And for the psi star, the complex conjugate, I'm going to stick that in there. And it's going to look a little long at first. This is all one equation down here. But notice I've got psi star minus IH bar V psi. And here I've got plus IH bar V psi star psi. I do have to move, that is, switch the order of the V and the psi star to show that those terms cancel, but I can do that. Even though you often in quantum mechanics have to worry about what order things go in, these are just functions, so you can switch the order. I didn't ignore complex conjugating V anywhere because it's a real function, so V star equals V. That means that I can collapse what's on top, which is the same thing that was on the end of the last page, by crossing out those potential terms, and I end up with this prefactor times spatial derivatives of the wave function. Now that's not what the time derivative of the probability density first looked like, but it should look familiar anyway, because it's what the space derivative of that new function j looked like. The minus sign's on the other term, so this is of course minus dj dx. Okay. So what I've just proven is that that new function j that I just tossed out there and gave a letter to, the space derivative of it is the negative of the time derivative of the probability density function. This is when I should start calling j what I wanted to talk about when I put it in the title, the probability current, or really probability current density. This gives us what they call a continuity equation. You may or may not have run into them before, but continuity equations you will run into in many upper division courses because there are similar things for fluid mechanics, for electric current, and for heat flow and thermal energy. Actually, there's more context if you go further in physics. And essentially what it says is that, in this case, probability density, what you lose at one place as a function of time is equal to the negative of how much is flowing to that place, or you might say how much is flowing out of that place, which is the natural way to think of it with fluids or heat, which I think are kind of intuitive that there's such a thing going on. This is saying there's the same thing for probability density in quantum mechanics. One of the things about that is it actually suggests that the form of the Schroedinger equation solutions, that is, those wave functions psi, are separable forms. That is, they're a product of a function of only space and a function of only time. You knew that. We've done that before. You probably did that in the previous course. I do have a video, which I'll link up in the corner here, showing how to do that, because the way to prove that, not just suggest it, but prove it, is a classic method for differential equations. You try it. You take a function of space times a function of time, you stick it in and see what you get. And it works. I did want to note that we never approached the solutions for classical waves that way. We treated them quite differently, and in fact we never put, at least in the way we do the courses in order, in the intro versions, we never put a potential in for classical waves. So this is kind of different from stuff you've seen before, even though it's still just wave equations. You might want to wonder whether that leads us where we're going with this. As I said, a lot of it was about mathematically closing the loop. So now I think I've motivated the reason we tried separation of variables, which you've seen. But separation of variables is really important, and if you don't know it well, you should review that other video that I linked, I just mentioned before. It was easy in that video to separate the functions for x and the function for t in the 1D time dependent wave function. The math gets a lot harder when you start trying to separate things for spherical coordinates in 3D, but we will do that in this course. The concept of probability current will come back on its own in the way we do the course next semester, we call it Physics 462, when we talk about scattering theory, which is a standard thing to talk about somewhere in the upper division undergraduate quantum mechanics class. So you will need this concept and need to go through it more deeply and understand it better at some point. And for us, that's next semester, so we'll cover it again then. Frankly, that's all I really wanted to cover now. Thank you for watching. Please go back to studying.